Hello everyone, I hope you're all doing well. So in today's video, we're going to go through the 2024 VCE Maths Methods Exam 1 that just came out today. I just want to say congratulations to the class of 2024 for trying your best. I hope this exam was well. It wasn't too bad. I had a talk to some of my students and they told me that everyone had mixed reviews. Some said it was easy, some said it was quite hard. I have no idea. So this is my first time trying it out. I hope everyone succeeded, try their best, and yeah, good luck for tomorrow's exam, guys. Get enough sleep, and good luck with that. I hope you guys succeed with that too. And yeah, guys, just like always, guys, before I start this video, if you guys want private tutoring in specialist methods, physics, or chemistry, you can always email me through this email. Yeah, guys, let's smash through this video. So, first question is a normal derivative question. Let y be e dx cos 3x. Find dy dx, which is 1 mark. Easy, you just have to give the answer. So we know we're going to be using the product rule. So that's u and v. So it's going to be dy dx. So it's u, which is e to the x. Then it's v dash, which is the derivative of cos 3x, which is negative 3 sine 3x, plus v, which is cos 3x, times u dash, which is just e to the x again. So rewriting this nicely like this, negative 3 ex sine 3x plus ex cos 3x. And that's it. Have I made any silly mistake anywhere? Nope, looks great. So that's your first answer. Really nice question there. Okay, typical. So, okay, we have f of x and it's a logarithm. Find f dash of 3. Very, very easy question. So to derive any logs, we know that d dx, this is the formula. When we derive any in the form of a log, so if you have a function in of a log, we know that the derivative is just f dash of x over f of x. That's it. So this is using this rule. So let's find, the first mark comes from actually finding the derivative, which is what? So derive the inside, which is 3x squared minus 3, and rewrite the that part at the bottom. And so we're going to then sub in 3. That's 1 mark, and then of course the other mark comes in when you sub in 3. So it'll be 3 to the so 3 squared is 9 minus 3 all over. So 3 to the power of 3 is 27. So 3 times 3, minus 9 plus 2. So 9, 18, 27. 27 minus 3 is 24. All being divided by 29 minus 29. So wait, 27 plus 2 is 29. 29, yep. So it's, what's happening to me? Oh my god. So wait, 29 minus 9 is 20. That becomes 20 here. So, of course, because they're both even number, just half both of them. So 12 over 10 and half it again because they're still even numbers. So 6 over 5. That is that answer here. Really nice question. I mean, that's really nice. Not too bad. Next question, question 2. So, yep, nothing else. Okay, so question 2. Consider the simultaneous linear equations. These are where x and y are element of all reals and k is a real constant. Determine the value of k for which the systems of equations has no real solutions. Okay, what is the condition for them to have no real solutions? We know for them to have no solutions, they must be parallel. They must be parallel like this. Well, what are the properties? Well, we know that if they have to be parallel, like we said, but also their y-intercepts have to be not equal, because if they are equal, they're gonna be on top of each. What's happened there? They'll be on top of each other, and they'll create infinite many solutions, and that's not what we want. So these are the two properties that we must have for the values of k. Yeah. For this to be no real solution. So let's do it. So first of all, what I'm going to do is get these in the form of y equals mx plus c, because I can easily see the gradient and the y-intercept. And so I can use that to compare and stuff. So let's do that. So for this one here, I'm going to write it down because quite not the best quality here. So let me just write it down. Looks like this. Equals basically k plus 4. And let's rearrange it to get y equals. So what I'm going to do is I'm going to bring this to the other side and then bring this to y to make it positive. So 3kx minus k plus 4 is equal to 2y, and divide both sides by 2 to get rid of that 2. Done. So now we can easily find the gradient, because remember the gradient is the one next to the x. Can you see this one has the x part here? So it's 3k, of course, don't forget divided by 2. So I'm going to call this M1. So that's 3k divided by 2. And the y-intercept is what? Remember, it's what's left over. So which is, come on, what's that happening here? Okay, which is negative k plus 4 divided by 2. Okay, done. So let's do the same for the other one too. So what I'm going to do is I'm going to rewrite it, the other one too. K minus 4x plus ky equals negative k. And so I'm going to, of course, solve for y. So what I'm going to do is I'm going to bring this to the other side. So it'll be ky equals negative k minus k minus 4x, and divide all this by k to get rid of this k here. Now look, same thing, it's like y equals. So let's find the gradient. I'm going to call this m2. So the gradient is what's next to the x, which is that negative k minus 4 over k. The y-intercept, so the y value is just negative k over k, which is just negative 1. Beautiful. So done. So let's look at the first condition. The gradients must be equal. So let's equate these two gradients over here. Let's equate them. So it's going to be 3k divided by 2 equals negative k minus 4, all being divided by k. I'm going to cross multiply these, so cross multiply them like that. So that'll be 3k squared equals negative 2k minus 4. And so expand it out. So negative 2k plus 8, bring them all to one side, so this side, plus 2k minus 8. And I'm going to find two things that I'm going to factorize these. So 3k, k, so two things I'm going to is 4 and 2. Yes, 4 and 2 works. Putting a negative here works, yeah. So because 6 minus 4. Yep, 2k, beautiful. So it'll be factorized. This quadratic gets factorized to this. Equals 0. Hence k equals 4 on 3. And k equals negative 2. So these are the two values of k for which we will have the same gradient. But be careful. Do not assume that these are the answers, because remember, the y-intercepts also have to be not equal. So how do we check that? Well, we sub them into here. So let's come here. Let's try the first one, which is negative 2, because that's the easiest. It looks like to sub in. So let's write y1 here. Can you see this part here? So I'm going to sub it in there. Negative, so k is negative 2 in this case, plus 4 divided by, wow, do you see that thunderstorm right there? Crazy. Divided by 2. So 4 minus 2 is what? It's 2. Negative 2. It'll be negative 1. This value will be negative 1. And so y2, you know how we already know y2 is negative 1. They have the same y-intercept. What happens if they have the same y-intercept? That's not what we want, because we want different y-intercepts. So this actually results in infinite many solutions, which we have to actually reject that y equals negative, in this case, negative 2. So we want to reject. So why am I saying yk equals negative 2, as it gives infinite many solutions. Infinite many solutions. So we also have to check the other one. Well, the other one is k equals 4 on 3. Let's check it too. So y1 is negative. So if I sub 4 on 3, so it will be 4 on 3 plus 4, all being divided by 2. And of course, y2 is just negative 1. Let's see what that's going to equal. So 12 on 3, which is 16 on 3. What's negative 16 on 3 divided by 2, which is just times it by half? It's negative 8 on 3. y1, this part will be negative 8 on 3, which is not equal to y2. So y1 is not equal to y2, which is what we want. We don't want them to equal. So this actually meets that condition. Hence, the only solution for no solution, hence, is k equals 4 on 3. Hence, k equals 4 on 3 for no solution. That is your only answer. Beautiful. Done. There it is. Not too bad. So, hope that makes sense. Beautiful. Next question. Question 3. It says, let G, okay, we know all roots except negative 3, and it's a truncus. Of course, that's its maximal domain. On the axis below, sketch the graph of g of x, label all the asymptotes with the equations and the actual intercepts with the coordinates. Really, really nice question. So let's first find the asymptotes. To find the asymptotes is really quite easy. You just solve the bottom part to be equal to 0 and, solve for x, which is x equals negative 3. That's already one asymptote. So Just draw that. So x equals -3. And the horizontal asymptote is y equals -2. It's basically like the hyperbola, how you check for it. So yeah, y equals -2. Done. Now we're gonna, of course, get the x and y. Wow, what the hell has just happened? Wow, that's really hard. Yeah, damn, it's crazy, the fun storm. So y equals, so we're gonna find the y, of course. So it's just by subbing x equals 0, which is y over 9 minus 2, which is minus 18 over 9, which is negative 17 over 9. So that's the y-intercept, which is basically like negative 1.9. So it's around here, somewhere around here. So that's the y-intercept, and of course we want the x. Remember, how does a truncus look like? Just don't forget what a truncus looks like, actually. So, actually, why did I rub that out here? A truncus, this is a positive truncus, by the way. A truncus looks like this, looks like that. So, what about the, we know it's gonna look something like this, by the way, but we need to find the x-intercepts also. So to find the x-intercepts, you know what we do? We just have to solve for, g of x equals 0. So, g of x equals 0, so putting 0, bring that 2 to the other side, actually. 1 over x plus 3 squared, which is 1 over 2 x plus 3 squared, which, square root both sides, 1 over root 2, and then minus 3 on both sides equals x. So that is basically, which you can write it as just -3 plus or -1 over root 2 sounds that sounds actually more better writing it like that. Okay. So that's your x-intercepts. And actually like makes sense. It does make sense. Like, for example, we know that writing in this form is so much easier because, so think of it like this. We know that here's -3, yeah? It's saying, hey, -3 minus 1 over root 2. So it's making it more negative, but 1 over root 2 is like what? Like, it's very small. It's like 1 divided by 1.4. So it's like 0 point something. So it just, yeah. So it's around here, somewhere around here, let's say. And they're equally distant. So this one has to be equally distant to, like, imagine this is a line. They have to be equidistant because you're saying, hey, -3 minus 1 over root 2 and -3 plus 1 over root 2. So, yeah. And then, yeah, just line them up. So nicely line them up. There it is. Line them up like that. This one also too. All right. So nicely lined up. All right. So this one over here is, of course, let's label them up. 0, -17 over 9. This one over here is the positive one, so it's -3 plus 1 over root 2, 0. This one over here is -3 minus 1 over root 2, 0. A really nice part here. Have I labeled everything? Yes, so the equation of the actual intercepts, yes, that looks quite good. Next question. Determine the area of the region bounded by the line x equals -2. So let me just draw that. Where is that? So x equals -2 is like this line over here. So you might draw a straight line. The x-axis and the line and the y-axis and the graph of g of x. So basically this area over here. Just this area here. That's what we're trying to find. So let's write an integral. This is a not too bad, part, because it's just the integral from -2 to 0 of g of x. What's g of x? X plus, basically you can write it as just x plus 3 to the power of -2. Yep, minus 2 dx. Now be careful. This will give me a negative area. Remember, it's below. So I have to put a negative in front of it. And that's it. So I'm just going to, I don't like this part here. I'm going to rub that out. Okay, now let's integrate this. So that's going to integrate to what? So you remember how to integrate. So it's going to be 1 over, derive the inside, which is 1. Add 1 to this power, which is -1. Rewrite it to the new power, which is -1. Then integrate this one also, which is -2x. Okay, so this part here, this becomes negative. Like -1 over. -1 over, put this at the bottom. Put it at the bottom right there. All right, -1 over that basically. Put this a little bit closer. From -2 to 0. So I'm going to start subbing in 0 first. So -1 over 3. And then you sub in 0 to the other one will be 0. Minus, and you sub in -2 now. So 3 minus 2 is 1. So it's 1. Minus 2, -2. Close bracket. Close it like that. So this here will be just -1. this part here would be positive 4. And this will be basically 3. This will be 3. So we're nearly there. What's that going to be equal? So what's negative 1 over 3 minus 3? That's negative 1 minus 9 over 3, which is negative 10 on 3. And that's going to give us positive 10 on 3, which is units squared because it's area. Now, have I made any mistakes here? So any algebraic mistakes? Negative 10 on 3. No, looks good. Looks good. Done. I'm just going to rub this part out. Done. Not too bad. So right now we haven't reached a really hard question, so this is good. This difficulty. Question 4. Let x be a binomial random variable with, with the n is 4 and the probability of success is n over 10. Find the standard deviation of x. Really easy. So we know that the standard deviation of a binomial distribution is just the square root of np1 minus p, which is what? So think of it, okay, what's n? Well, we know n is 4, p is 9 on 10, 1 minus p is 1 on 10. So it's going to be equal to, so 9, 18, so it will be 36 over 10 times 10 is 100, and the square root of 36 is 6, and the square root of 100 is 10, so that'll be 3 over 5. That is your answer for that one. Next question, find the probability that x is less than 2. Okay, because it's binomial, it's really easy. We can actually just draw a table to represent this. Oh, sorry, let me draw a nice table here. Okay, so let's draw this table. Oops. Where, of course, you start at 0, you have 0, you have 1, you have 2, you have 3, and then you have 4. Remember, because 4 is the max. So we're trying to find the probability that x is less than 2. So this part over here. So which is just basically the probability of x equals 0 and probability of x equals 1. So we can write that down here. Probability that x equals 0 plus the probability that x equals 1. All right. So what's the probability that x equals 0? Easy, just use your binomial rule. So remember how it's so 4 choose, it'll be 4, choose 0. Probability of success, which is 9 over 10 to the power of 0. Probability of unsuccess, which is 1 over 10, which is 4 minus 0 to the power of 4. Plus, and do that for the probability that x equals 1. So 4 choose 1. Probability of success, 9 over 10 to the power of 1. Probability of unsuccess, which is 1 over 10 to the power of 4 minus 1, which is 3. So 4 choose 0 is, we know it's always 1, and anything to the power of 0 is 1, so that's that. All right, so let's just move this here. Okay. So should move it down here. Yep. So we know basically that 4 choose 1 is 4. We already know that's 4. Bring that 9 actually out. You can actually bring that 9 out. And this becomes a 1. And then these two multiply to make 1 to the power of 4. So this is actually easier. And then 9 times 4 is 36. So 36. And you know how that's 1? So like 1 times. Yep. So because they have the same thing, they can add up. So it'll be 37 times 1 over 10 to the power of 4, which is what? So 37 times, what's 1? Basically, 1 to the power of 4 is 1. 10 to the power of 4 is what? So 10 squared is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. So it's actually 10,000, which gives us your final answer as this. 1, 2, 3. 10,000. Done. Not too bad. All right. Beautiful. So let me rub this out. I want that. Okay. Not too bad. So next question is question 5. So question 5 says, the function h from 0 to infinity h of t, which is a hyperbola, models the population of a town after t years. So use the model h of t to predict the population of the town after 4 years. Easy. So to do that, well, it's just summing 4 years. It's in terms of, so h of 4, which gives you 4 plus, so basically 3,000 divided by 4. So 4 plus 1 is 5, which gives you 600. 600 is your population. Not too bad. So next question. A new function h of 1 models a population where h1 of 0 equals h of 0. What this tells me is, because you know how h of 0 represents the initial population, which is what? 3,000 because you sub in t equals 0, it's just 3,000 divided by 1. So the initial population, this here, is 3,000. h1 of 0 also means that the initial population for your new function, h of 1, has to be 3,000 also. They basically start with the same population. This is what it means, this part here. All right, so that's what that means. But h1 decreases at a half rate of h at any point in time. So basically, like, its derivative is halved. State sequence of two transformations that transforms h to this new function h1. All right, so, okay. So the most easiest case is, okay, it says h1 decreases by half the rate of h at any time. So basically meaning that h1, like the derivative of it, because it's, yep, h1 of t is equal to half the rate of h of t, basically. That's what it means. All right, so let's actually find h dash of t first. And we can just move on with that. So h dash of t is what? H dash of t is, so before even doing that actually, I'm going to call it just h of t. I'm going to write it in a nice form. So 3,000 t plus 1 to the negative 1. And so when I derive it using my derivative laws, this is a constant, that 3,000. Remember, you bring the negative 1 in the front, this negative. You derive the inside, which is just 1. You rewrite it to the new power, which is negative 2, which is just this, basically. If you put this basically to the power of 2 here. This becomes to the power of 2. Done. All right, this is that. So basically, this, because we know this expression, so if you times it by half, it will give us h1 dash of t. So times it by half, which gives us negative 1500. So yep, t plus 1 squared. And what we can do from here is anti-derive it to go back to the original. So we can actually get the equation of h1 of t, basically. So if you anti-derive that, so h1 of t, so imagine, okay, we're anti-deriving this, so just make this actually easier by putting it over here, making it negative 2. And so imagine anti-deriving this here. So it would be, remember that's the constant, so don't worry about that. Remember how it's 1 over. You add 1 to this power, which is negative 1. You derive the inside, which is just 1. You rewrite it to that new power, which is negative 1, which is basically negative becomes positive. These cancel out. And then, yeah, this thing here just goes to the bottom. Oopsie, what happened there? This thing goes at the bottom. It looks like this. Perfect. So, wait. So, h of t looks like this. They look the same, but it's just halved. It's just dilated by a factor of half. Easy. Perfect. That's what it is. So, I'm just going to put this here, by the way, so I don't forget about this here. So, I'm actually going to write it here. So, already I know what sequence of transformation already 1 is. So, to get, so if I dilation by a factor of a half, you can say parallel to the, in this case, y-axis, but it's h-axis basically. Or you could say dilation by a factor of half from the t-axis. Your choice, you could use whatever. But I think, yeah, that's it. So what that does, okay, but there's a state 2 transformation. It's not just this one. So, okay. All right, yes. So if I did that, we get the same equation. But, we also have to meet this condition where the initial populations have to be the same. Because you got to remember, this one over here, the initial population when you sub in 0 is 1,500. This one's 3,000. So how do we make them the same? Well, kind of think of it like this. If I had a graph of it, I'm going to make a fake graph, by the way, just to kind of explain this a little bit in scenario. So imagine this is your initial population. It's 3,000 and it's decreasing, yep, like that. So this is your h of t. That's your, yep. And then this one's like that. It looks like that, and that's 1,500. That's 3,000. So right now, basically, what's happened is, you know, h of t, we've dilated by a factor of half, which now looks like this over here. Now, how do we make it have the same, initial population? You know, it's 1,500. How do we make it have 3,000? We want to make sure it has 3,000. Don't we just translate it 1,500 units up? That's it. That's your next one. So translation of 1,500 units up. Done. That is it. That's that question there. Not too bad. So in the town, 100 people were randomly selected and surveyed, with 60 people indicating that they were up and happy with the roads. Determine the approximate 95% confidence interval for the proportion of people of the town who were unhappy with the roads. Use Z equals 2 for this confidence interval. Really nice question. So let's do that. So our p hat is what? Remember, your p hat is 60 over 100, which is basically, take that out, 6, which is 3 over 5, basically. Because divided by, yep, 3 over 5. So using our confidence interval formula, remember how it's p hat, so it's 3 over 5 minus z, which is 2, square root of p hat, which is 3 on 5, times 1 minus p hat, which is 2 on 5, over the n, which is 100 people, and then it's the same in the other case. So, but there's a plus square root 3 on 5, 2 on 5, all being divided by 100. All right, so let's just simplify this whole surd here. So if I kind of a little bit simplify it, it's basically 6 over 25 divided by 100. And so that simplifies to same as 6 over 25 times 100, because 6 over 25 divided by 100, yep, that's what it'll become. And so that will simplify to what? It will simplify to square root of 6, and the square root of 5 is 5, and the square root of 100 is 10, so it's actually 50. This part here is 50. So imagine I'm going to just replace all these parts here with that. Square root 50. Also the same with this one here. Okay. Square root 650. So, all right. Now, what's going to happen is this 2 goes into that 25 times. So that part here, you can write that as 25. Just 25. And the same with the other case. So this 2 simplifies that to 25. All right, so 25. Why is it? Okay, 25. And so, yeah, it's just 3 over 5 minus root 6 over 25, which becomes what? So what's 3 over 5 minus root 6 over 25? So that will become, so if I multiply both sides by 25, it will be, so wait, 25, 15 will be basically 15 minus root 6 over 25. 25, and then this will be the same basically, but will be a plus root 6 over 25. All right, that looks good. So, yep, that's that one. All right, let's smash with another question. Done. Nope, it's the same. Yeah, it's the same questions. A new sample of n people results. So it results in the same sample proportion. So it's still the same sample proportion, which was, what was it again? 3 over 5. 3 over 5. Okay. So find the smallest value of n to achieve a standard deviation of root 2 over 50 for the same sample proportion. Easy. So we know that the standard deviation is root 2 over 50. And we know that the standard deviation formula is, do you remember, it's the square root of p hat 1 minus p hat over n. So in this case, what's our p hat? Well, our p hat is the same. So it's 3 on 5 times 2 on 5 over n. And that's what we're trying to find, the n. Remember, this simplifies to 6 over 25. Which is 6 over 25n. Okay, so you can basically, what we can do is we can like this part here, we can write it as just like, because you know that 25 can come out, yeah, so it'll become like root 6. So root 6 so root 6 over 5 root n, because you've got that 25 and it comes out. Yeah, and the other ones are still square rooted. Okay, so that becomes root 6 over 5 root n. What happens is 5 can go into that 10 times, so that simplifies to 10. And we can actually cross multiply here. So cross multiply here, cross multiply and cross multiply here. that gives me root 2n equals 10 times root 6. So square root both sides, square both sides to get rid of that, which is 100 times 6. Divide both sides by 2, which is 103, which is 300 basically. That's your sample. Done. Your new sample is 300. Nice, not too bad. Next question. Solve 2 log 3x minus 4 plus log 3 of x equals 2 for x. Really typical question that you now, I haven't seen it, you know, it used to come in like the 2016 papers and stuff, but yeah, now it's great to see these questions, the log questions back. So what we're going to do is take that 2 to the power inside. So it'll be x minus 4 squared plus log 3 of x equals 2. What happens when two logs add? They multiply. The insides multiply. So it'll be log 3 x minus 4 squared equals 2. And so it'll be 3 squared, because I'm going to make this exponential. So 3 squared equals x minus 4 squared. And that 3 squared is 9, by the way. Yep. So 3 squared. So yeah, 3 squared is 9. Yep. Equals x minus 4 is just x squared minus 8x plus 16. Expanding that out gives me x to the power 3 minus 8x squared plus 16x, which gives me x to the power 3 minus 8x squared plus 16x minus 9 equals 0. And this is a cubic. Now, I'm going to be honest with you, we have to use what we call, I fully forgot what it is, the null factor theorem, where we start guessing values, what roots, and they should be equal to 0. So it always start with like 1, negative 1, 2, negative 2. Always do that. So let's sub in 1. 1 minus 8 plus 16 minus 9. What's that going to be? That's going to be... That's going to be negative 7. That's plus 7. Yes, that's actually 0. That's actually 0. That's great. So 1 is a root. So we can write it as like, yeah, so 1 is a root. So we can write it as like, in terms of fact, it'll be x minus 1 and some rubbish. Now you can use long division. Now there's actually a quicker method. Which is called synthetic division, which I'm going to use, to be honest. So synthetic division, what I'm going to do is I'm going to just place all those constants in here. So you know how it's 1, negative 8, 16, negative 9. What was the root? Well, it was 1. You know, the root was 1. So bring this down here. So what's 1 times 1? That's 1. What's negative 8 plus 1? That's negative 7. What's negative 7 times 1? Negative 7. What's these two add up again? Which should be positive 9. What's 9 times 1? It's 9. And of course, you add these up, that's your equal 0, because your actual... It has to be equal to 0. You have no remainder. So then this becomes, these are your new coefficients for, so it'll be x squared minus 7x plus 9 equals 0. So much more better. All right. Actually, let me just, oops. Okay, we're nearly there. Now, I'm going to try to factorize this one over here. I'm going to try to actually factorize this part here. Can you factorize it? X. So 9 is like 9, 1. No, you can't actually factorize it. I just want to check that with a discriminant. Does it actually have solution? So remember b squared minus 4ac. I also want to check it. So it'll be 49 minus 4ac is 9. 49, 9, 18, 27, 36. Yeah, it does actually. It's positive. Okay, so it does actually have. So we're going to have to use the quadratic formula here. So remember the quadratic formula is negative b, which is negative 7, plus or negative b squared, which is 49, minus 4a is 1, c is 9, over 2a, which is just 2. So it'll be 7 plus or negative, so 49, it was 49 minus 36, what was it? Yeah, which was, so 4 plus 9, it's 13, so root 13 over 2. This is your roots, so done. So we can actually rewrite this whole thing as x minus 1. So because these are roots, so we can say it's like x minus 7 minus root 13 on 2. And we can write this as x plus, 7. Oh, why am I tweaking, bro? So yeah, wait. It's supposed to be minus here. Wait. Yep. So x minus 7 plus root 13 on 2. Because when you solve these, yep, they should. Yep, that's equals 0. We just solved those. Okay. So I want to double check everything here. So Yep, it'll give me that. And then if I solve that, it'll give me that. Wait, looks good, looks good. Okay, so these are all our roots. So it's, of course, x equals 1. X equals basically 7 minus root 13 on 2. And x equals 7 plus root 13 on 2. Now be careful, remember logs are a little bit different. We need to check these conditions, like the insides. So first of all, this first part here, you remember how in a log, the inside has to always be positive, greater than 0? Well, are these all positive? Yep, this one's positive. Is this one positive also? So that's positive, of course, but this one, so 7, root 13 is what? We know root 13 is between what? So root 13 is between root 16 and root, so wait, yeah, root 16 and basically root 9, which is between, like, so basically between, it's between, like, let's say 3.5. So minus 3, yeah, it's also positive. These are all positive, basically. But, okay, so it does meet the first part, but does it also meet this part here? So remember here, also this one, so x minus 4 also has to be greater than 0. So x must be greater than 4. So all the values have to be greater than 4. Which ones are that? Yep, that x equals 1 is wrong because it's not greater than 4. Remember, it also has to meet this condition. So not that one. This one's great because remember, it's 7 plus, so what's happening here? 7 plus, remember root 15, we said it's like 3.5. Estimate divided by 2. Yep, that's greater than 4. This one over here, so we're saying 7 minus like 3.5. Nope, this is not going to be greater than 4. So we also have to reject this one over here too. So these are all the ones that we're going to have to reject. So let's write down why we're going to reject them so we can give a reasonable answer. Okay, reject x equals 1 and x equals 7 minus root 13 on 2, as x has to be greater than 4. Hence, your final answer is 7 plus root 13 on 2. That's your only solution, actually. So x equals that. Beautiful. Not too bad. All right, next question. Question 7, let's have a look at this. Part of the graph from negative pi to pi of f of x, x sine x is shown below. I'm kind of tweaking because it's saying negative pi to pi, but it's showing me 0 to pi. Could it be a mistake? Don't know. So x sine, okay. Use a trapezium rule with a step size of pi on 3. I don't know why they're using the word step size. They should use width. Step size is like in specialist when you're using Euler's formula. Yeah, step size means just width, if you're wondering. So the width of pi on 3 determine approximation of the total area between f of x and the x-axis over the interval 0 to pi. All right, so beautiful. So let's draw trapeziums here. There, that point, that point. Let's just draw these nice trapeziums. That's going to be here. Going to be one like that. This one over here is going to be like this. Okay, this one over here goes like that. Okay, this one over here goes like that. Okay, so you remember the trapezium rule is so easy. It's just width divided by 2. And you remember the beginning value. So you know how that's the beginning and that's the ending value, which is pi. Is they're going to start off f of 0 and f of pi, but whereas the middle values are going to be always 2 of f of pi on 3 or 2f of 2 pi on 3. So let's try it. So what's the width? Well, we know the width is pi on 3. Yep, pi on 3. Remember we said divided by 2, which becomes pi on 6. Because, yeah, times it by half. Yep. So pi on 6. So you remember, so starting value is f of 0. Always the middle values, these two middle values are going to be 2f. So 2f of pi on 3 plus 2f of 2 pi on 3. And you're up to the ending value, and that's just going to be f of pi. Done. So we just got to simplify this. We know f of 0 is straight away 0 because it just shows us here anyway. So pi on 6. Or does it? Oh, the equation's here. Yeah, if you sub in 0, it's 0, yeah. So just, yeah, don't assume. Just look at the, yep, so that's 0. What's f of pi on 3? So it's pi on 3. And then sine pi on 3 is root 3 on 2. So it's 2, so it's like 2 times root 3 pi on 6, which is basically root 3 pi on 3. So this one simplifies to that. Next one is 2f of pi on 3. So what's first f of 2 pi on 3? So it'll be 2 pi on 3. Don't forget that 2 here. I'm going to just leave it there. And then sine 2 pi on 3. What's sine 2 pi on 3? So sine 2 pi on 3, you can write it as sine pi minus pi on 3, which is in that right quadrant. So yeah, sine, it's the same as sine pi on 3, which is what? Root 3 on 2. These can cancel out. So it's just 2 pi root 3 over 3. Is that right? So 2 pi root 3 over 3. That sounds good. Plus 2 pi root 3 over 3. What's f of pi now? So f of pi, I hope I haven't made mistakes. These are just, I think I'm a little bit going quick with this. Pi. So pi, what's sine pi? Sine pi is 0. Because sine is 0. So you only left out with these. Okay. Now I just want to check the one that I just did here, the f of 2 pi. Because I did it really, really quickly and I wasn't even, okay. So it's 2 pi on 3, sine, it's basically the same as root 3 on 2. Cancel these out. 2 root 3. Yeah, that looks correct. That looks correct, yeah. All right, so let's finish this. So what I'm going to do is, now expect, like, can I simplify anything? Oh, yeah, I can actually. What am I doing? I can add these two up, which becomes 3 pi root, wait, so 2 pi, yep. So so it'll be, 3 pi root 3 over 3. So these cancel out, which is root 3 pi squared on 6. So that's that one, units squared. Done. That looks good. Perfect. Yeah, that looks not too bad. So next question, find f dash of, find f dash of x. Easy. So it was just a product rule. So, okay. So just let's do it here. F dash of x is what? So remember, this is your u and this is your v. So u is x, v is deriving sine, which is cos, plus then derive sine, which is just sine of x. So no, like v, which is sine, and then derive x, which is 1. So basically it's this. I'm just going to kind of take this here and copy it. Cut it. Put it here. Okay, paste it here and put it right down there. Nice and done. Only 1 mark. So yeah. Next question. Okay, done. So next question, determine the range of f dash of x over the interval pi on 2 to 2 pi on 3. Okay, so the range of f dash of x. Wow. So, okay, we need to think about this. All right. So pi on 2 to 2 pi on 3 is where? I'm going to rub this part out. I don't need this anymore. So pi on 2 to 2 pi on 3 is here. So pi on 2 is around here. Yep, here. To 2 pi on 3 are here. So, yep. Of course, it's going to be closed circles. Remember, it is going to be closed circles. We're not looking at endpoints here. So if it was endpoints, let's say if it was endpoints and stuff, there'll be open circles. But because we're looking at from, 2 pi, pi on 2 to 2 pi on 3, yeah, they're inside, yeah. So, okay, if I the way that I would do this is, okay, I'm going to just kind of think of how the graph would look. So for example, if this was, let's say, pi on 2 here, pi on 2, and this part here is 2 pi on 3, yeah? Actually, let me draw a nice graph to kind of represent this much more nicer. Why did I group that? Cut it. Okay. So I'm going to draw it in such a more nice. Okay. So imagine, okay, I draw this and this is your f dash. Because we already got the equation, so we can actually do a lot of, so imagine that's f dash of x and that's x. So imagine that this point here is pi on 2 because we're only going from pi on 2 to 3 pi on 2. So, okay. So what's the value of pi on 2? That's the first case. What's the pi on 2? We can sub it in here, actually. Just sub it in here. So pi on 2 is what? So you can say pi on 2. What's cos pi on 2? That's 0, isn't it? Yep, it is pi. Yeah, it's 0. And so what's sine pi on 2? Sine pi on 2 is 1. So yep, so at pi on 2, it's 1. The y value here is 1. So imagine this here. Closed circle, 1. And it's going to be a closed circle. Remember, we said it's not the endpoints. Yep. And what about 3 pi on 2? If I sub them 3 pi on 2, 3 pi on 2, what is cos 3 pi on 2? You can write it as cos 3 pi on 2, is it? 2 pi. Oh my god, what the hell? Because I'm that, oh, yeah, man. It's 2 pi on 3. Okay, it's 2 pi on 3. What am I doing then? What 3 pi on 3? Okay, let's rub that out. Okay, so 2 pi on 3. So 2 pi on 3 cos, you can write, is it pi minus pi on 3? You can write it the same. And sine pi minus pi on 3, the same as that. It's 2 pi on 3. So pi minus, this will be negative 2 pi on 3, cos pi on 3. What's cos pi on 3? Half. Plus, what's sine? Basically, sine pi minus pi on 3 is just the same as sine pi on 3, which is root 3 on 2, which is negative pi on 3 plus root 3 on 2. That's the y value. So root 3 on 2 minus pi on 3. Wait, so is it a negative or positive value? So negative pi on 3 is like negative 1 point, I don't know, let's say it's 2 or something. Because it's like, imagine like negative, yeah, so I don't know, like, yeah. And then root 3 is 1 point something. You divide it by 2, it's going to be like 0 point something. Yeah, it's going to be something like 0 point plus 0 point. Yeah, it's going to be a negative. Like, I don't know, let's say 0.4. It's like 0.4 minus 1. It's going to be a negative anyway. So it's actually a negative value. So this part would be, I don't know, let's say here. And that value here is that root 3 on 2. So root 3 on 2 minus pi on 6. Pi on 6 with it? Or pi on 3? Minus pi on 3. Okay, there it is. And of course, it makes sense. You can see how this here, the gradient was actually steep. You can see how it was steep, but when it reaches, it's becoming less steep because it's reaching a turning point, close to a turning point. So it's actually decreasing, like this. Look like this. There it is. It'll look like this. And you can see the range is actually from root 3 on 2 minus pi on 3 to 1. Hope that makes sense. So, yeah. That does make sense. Yeah. So it's only 1 mark, so we have to just write the answer. So root 3 on 2 minus pi on 3 to 1 inclusive. So let me check that again. Root 3 on 2 minus pi on 3 to 1. That looks good. Yeah. So next question. Yeah. Next question. Hence means using this question over here, verify that f of x has a stationary point at from pi on 2 to 2 pi on 3. I mean, that makes sense. You can actually see it over here. So around here, there is a stationary point around there. But all right, nah, it's actually easier than you might think because we're using this. I can use this graph here to actually explain it. This graph actually is so useful because let's think about it. Okay. Let's paste it here. How is this graph going to really help me? And I'll show you how cool this graph is. This is actually so cool to use this graph here. So it's saying verify that f of x has a stationary point between pi on 2 to 2 pi on 3. Now, we know for a stationary point to occur, doesn't f dash of x have to equal to 0? And we can see, you know how 2 pi on 3 is here? We can already see 2 pi on 3 is here. But we can see how it crosses between pi on 2 to 2 pi on 3. F dash of x is actually 0. So we can actually show that yes, it is actually, it does cross the x-axis. So we can just kind of explain it, yeah. Because it crosses it, there is, yeah, somewhere here, there's a stationary point. So let's just write for a stationary point, for a stationary point, can kind of describe it, for a stationary point, f dash of x must equal 0. So as as f of dash of pi on 2, so this value here is 1, and oh, what happened there? F of 2 pi on 3 is equal to root 3 over 2 minus pi on 3, which is basically, of course, less than 0. So like it's a negative number, which is negative, we'll say, which is negative. The graph of f dash must cross the x-axis, hence a stationary point. I hope that makes sense. Yeah, beautiful. I think using that graph is actually really much more easier. Okay, E. Is this E or C? I don't know, C, I think. On the set of x's below, sketch the graph of f dash of x on the domain negative pi to pi. Beautiful. Labeling the endpoints of the coordinates. You may use the fact that the graph of f dash of x has a local minimum at approximately, negative 1.1 to that, and the local maximum at that. Aha. Beautiful. Okay, negative 1, so wait, negative 1.1, so a local minimum, and a local maximum. Beautiful. That looks nice. That looks nice. Okay. Yeah, now we just need to graph f dash of x. Now, it's easy, actually, because remember we said, okay, there are some conditions. Wherever there are turning points, they're going to become our x-intercepts. So let's use a red color here. So this turning point here becomes the, I don't know, somewhere around here, x-intercept. This one over here becomes x-intercept. This one here around becomes x-intercept. Done. And remember how we said the endpoint, when you derive it, those endpoints become open holes. They become basically, yeah. So you know how these here, they're going to be open holes. But we need to find what they are, actually. First, let's find what their values are, because we have the equation, actually. So let's come back to this equation. I'm going to copy this equation here and bring it there. Copy. Let's write it here. Let's write it here. Okay. So what's the, because we need, it's saying label the endpoint. So you know how it's negative pi, what would it become here? So what's f dash of negative pi? So it'll be negative pi. What's cos, but it's cos negative pi is just cos pi. And that's negative 1, actually. And so sine negative pi is basically like negative sine pi. And negative, so sine pi is 0. So it's actually just positive pi. So this one over here will be positive pi, which is around here. Remember, it becomes an open circle. So, okay. Let's try then the other endpoint, which is pi. So f dash of pi is what? F dash of pi is pi cos pi. So we know that cos pi is negative 1. And sine pi, of course, is 0. So it's negative pi, actually. So negative pi is around, around here. So done. So we have these two open circles. And yeah, we can actually just kind of think of it. So let's think of it. You can see that from here to here, it's increasing. You can see how it's rising up. So the gradient's positive. So it's going to be above. It's going to be like above. Can you see how it's above? But then here, from here to here, it's decreasing. So it's going to be below. So it's going to be below, like that. And then you can see from here to here, it's increasing again. So it's going to be above, like that. And you can see from here to here, it goes below again because it decreases. So yeah, something like that. Done. And we can label those endpoints. Of course, we need to label those. Don't forget those. So negative pi to pi, pi to negative pi. And that's it. So sketch it, endpoints. And yeah, that's basically it. Nothing really, beautiful. This is the last question. Yeah, question 8. Let's get this paper done. I mean, it's a nice paper. It hasn't really been really crazy difficult. So G has the domain of all reals, and it's a cube root graph where K is an element of all reals except 0, and M is an element of all reals. Okay, beautiful. Let the point P be the y-intercept of the graph of G of X. Easy. Find the coordinates of P in terms of K and M. Easy. So isn't just P the y coordinate? So isn't it just G of 0? Which is what? So root 3 negative K plus M. Beautiful. So that's the value. Oh yeah, by the way, because it's a cube root, you can actually take that negative out. Putting it in front, actually. Put it in front if you want. So it's basically the coordinate is a 0. We could say negative root 3k plus m. That looks nice. Next question. Find the gradient of g at find the gradient of g at point P in terms of k. Beautiful. So what we can do here is we need to find the gradient, which is g dash of x. So what's that? So rewrite this. You know how it's just x minus k to the power of 1/3, yeah? Plus m. So when you derive m, it's just a constant. It gets off. So you remember how to derive these? So you bring the 1/3 to the front. You derive the inside, which is 1. You rewrite it to the 1, minus 1, like 1, from it. Which is what? 1 minus 3 on 3, which is negative 2 on 3. Negative 2 on 3. So that becomes that. So you can write it as like 1 over. Bring it to the bottom. So 3 x minus k over 2 on 3. Done. Perfect. Okay, cut. So we've got the gradient and we want to determine it at P, which is, remember, P, the coordinate of P, like x equals 0, it's the y coordinate. So G of 0, which gives you 1 over 3 of negative k 2 to the 3. Now think about it, actually. You can actually a little bit simplify this much further because, yeah. So yeah, absolutely you can simplify it further because negative k to the power, you know how to do like to the power of 2 over 3. Can we write it as to the power of 3, actually, can we write it as squared over 1/3? So like, you know, squared, then out bracket is 1/3, because when you multiply, it's the same as 2 over 3. And what's negative k squared? Doesn't that negative disappear and becomes k squared? And yeah, and which becomes k over 2 on 3. So you can actually rewrite that as that. I don't think you need to, but yeah, it looks nice. K 2 on 3. Beautiful. Next question. Let's just highlight that part here. And let's also highlight that part there. Okay, let me write this one. Okay, next question. Given that the graph of g of x passes through the origin, express k in terms of m. Really easy, just sub in 0, 0. That's sub in 0, 0, so that's going to be 0. Cube, okay, so if that's 0, it'll be negative k plus m. So what we're solving is k. Express k. So bring that negative m to the other side. We can write that as negative k 1/3. So how do I get rid of that 1/3? Don't I just multiply both sides? Like if I kind of like square, like not square, what we call the power of 3 on both sides. Think of that. What's going to happen is 3 times 1/3 becomes 1. So this actually just cancels out. What's negative m to the power 3? Just negative n to the power 3 equals negative k. And you may both become positive, hence k, which is m to the power of 3. Really nice. Done. 3 marks. Last question. Wow. Let the point Q be a point different from P such that the gradient of G at point P and Q are equal. So the gradients are equal. This is great. So you know how this is the gradient at P? The coordinate of Q has the same gradient, basically. Given that the graph of Y equals G of X passes through the origin, of course, so yep, find the coordinates of Q in terms of M. Not bad. So, okay, let's first do, okay, we're going to equal, so I know the gradient of Q is this, because they have the same gradient. So I can actually just, the formula of G dash is what? 1 over, so the gradient function is x minus k to the power 2 over 3, yeah? And it's going to be equal to this gradient because they have the same gradient. 1 over 3 k to the power of 2 on 3. So you can actually cancel those 3's out. Okay, that's nice. You can actually flip both sides. Like you can flip them. So because they're reciprocal of each other. So 2 on 3 equals k to the power of 2 on 3. And remember, I'm solving for x. What I'm going to do is I'm going to actually 3 to the, like 3 over 2 power everything. Because look at this. If I do that, 3 over 2 times 2 over 3 becomes 1. So this actually just becomes x minus k. And then this one here, same thing, 3 over 2 times 2 to the power 3 just becomes k. Hence, x is actually just 2k. That's your x coordinate for q, basically. And, okay, we've got the x coordinate for q. Let's also find the y coordinate because it's coordinates. So we just sub it back into g of 2k, basically. So what's g of 2k? All right, so 3, basically 2k minus k plus m, which is cube root, so that'll be k plus m. So that's the y coordinate, 3 cube root of k plus m. So the coordinates are, of q, of course, q, are 2k, and cube root of k plus m. Is that right? Given that the graph of G passes through the origin, find the coordinates of Q in terms of m. M. Oh, yes. Yep, that's easy. Because k is just, in terms of the origins, m squared. So we can just replace everything here. This becomes m squared. M cubed, sorry. What am I saying? M cubed. Let me move these to the other side. There it is. And this here, subbing k equals, so what's cube root of m to the power 3? It's just m. So m plus m is 2m. It becomes 2m. Done. And that is it, actually. That looks nice. That actually does look... Not a bad exam, actually. It really, like, compared to other following years, sometimes they're always harder, but this paper was all right. It was compared to other exams, it's actually easier. I hope you guys enjoyed this video. Please, you've learned something through it. And yeah, good luck with your tomorrow's exam, guys. Have a great day and bye.